The scenario we identified in order to demonstrate this technology is represented by a trip from Turin to the Teatro alla Scala in Milan. For demonstration purposes, when the system is booting, we can see the reference architecture layers loading up. The driver selects its profile and starts driving without selecting any option. When the speed exceeds a predefined threshold, in this case 20 km per hour, the interface automatically shows the default panel, which is defined in the user preferences. In this case, we have the free navigation panel. The system automatically calculates the cruise range based on the current fuel level and shows it graphically right on the map. Touching the button in the bottom left corner, it is possible to set up a new navigation route. Through the virtual keyboard, we can enter the new destination. A warning showing an insufficient fuel level for the selected destination is shown. This warning is initially ignored. The driver keeps driving until a new, not ignorable warning is shown. This warning informs the driver that the fuel level is lower than 5%. Tapping the fuel warning balloon allows the nearest gas station information to be shown. It is possible to visualize a 3D trip preview. Once the refueling is completed, a warning asking for the trip resume is shown. Tapping this warning causes the new route to be recalculated. When the car is close to destination, the systems automatically adapt the map zoom and recommend the available parking options, which are ignored at this moment. When entering an urban canyon, the GPS signal gets lost and the visual odometry algorithm starts calculating the interpolated coordinates, allowing the car to keep the correct position on the map. Tapping each of the available warnings on the bottom right side causes them to show each warning list. When approaching the theatre, the visual search algorithm finds a match between the side camera's stream and dedicated database. A visual search match warning is shown to the driver. Tapping the warning balloon, we can see the front camera stream right into the interface. The information regarding the theatre is shown using augmented reality overlapping the live camera stream. We can see multimedia information on this point of interest when the car stops, for example at a traffic light. The parking warning is shown again, and this time it is accepted by tapping it. It is possible to select the closer parking lot right on the map. The automotive demonstrator is described in this video in terms of hardware components, software components, and HMI patterns. Let's see the hardware components first. The automotive demonstrator can be set up both indoors and in-vehicle. The indoors setup consists of two main components: a server PC, where we can simulate the sensors or the entire scenario storyboard, and an Atom embedded board, where the actual Astute proactive interface software runs. The Atom board is completed with a touchscreen display, wheel and pedals to simulate the driving position, and a big screen running a background video of the car on the road to simulate driving distractions. In the in-vehicle setup, the sensors are not simulated anymore and are generated by the actual probes, dongles, and visual algorithms. In this setup, we also have cameras for visual odometry and visual search algorithms, as well as an internet connection to the remote augmented reality and point of interest database. Several ergonomics studies on the actual in-vehicle integration have been conducted. The user state devices can be connected either directly to the Atom board or to a dedicated PC device if necessary. Software components. The sensor simulation control panel runs on the simulation PC and allows each single sensor to be simulated individually. The storyboard simulator is used to simulate the entire scenario by sending the proper sensor data to the board automatically. The Astute proactive navigation system is built on top of the reference architecture and is completely user-centric. The architecture has been implemented using separated components communicating either via D-bus or TCP/IP. Since the communication protocol is standard, different components can be easily plugged in and interchanged. Sensors are connected to the aggregator through dedicated software packages via TCP/IP or D-bus. The user state software package processes the raw data of devices such as EEG connected via Bluetooth and throws out information such as drowsiness or stress levels. This information is used to update the model and thus the context. The visual search package runs on a separate device, detects possible building matches and sends the result directly to the aggregator. The visual odometry package works in a similar way and uses the last GPS fix to start calculating interpolated coordinates. The remote database contains several pieces of information, such as points of interest, images for visual search comparison, and even multimedia data. It is locally buffered when needed to save time. Two of the most important HMI patterns are the multiple warning and the meaningful sound management. We use categories, priorities, and specific screen areas to visualize the warnings on the display. The safety warnings automatically show up with a comic balloon, a sound, and a voice. Information warnings appear with no balloon, but with sound, and after a few seconds the balloon is shown, and if not managed by the driver, disappears quietly and automatically. Only a small badge number stays on the top of the icon, to keep this information in the driver's mind for future use. Other warnings have very low priority, and for this reason their balloon never shows up unless the driver touches the warning. Simultaneous warnings are managed by priority queue. This means that if a high priority warning is on the screen, touching lower priority warnings cannot show their balloons, and the icon on the safety warning shows the highest priority one, in this case the user state. Another important HMI pattern is spatial representation. In this case, for example, the cruising range is visualized directly on the map for the driver's convenience. Seamless connectivity is achieved at each level of the reference architecture through modularization and use of standard communication protocols. Components, such as new sensors, can be easily plugged into the architecture as long as they use Ethernet, Wi-Fi, and web services.